Just to do a recap on polynomials and their end behavior, for even degree polynomials, even with an exponent of 4, 2, 6, and so on, if it has a positive leading coefficient, here are examples, these two right here, with a positive leading coefficient, we know that our end behavior, both ends, will be up. Therefore, when x is going to negative infinity, y is going to positive infinity. When x is going to infinity, y is going to infinity. For a negative leading coefficient, both the end behaviors will be going down. So again, if x is going to negative infinity, y is going to negative infinity. If x is going to positive infinity, y is going to positive infinity. For an odd degree polynomial, so x to the third, x to the fifth, x to the seventh, with a positive leading coefficient, here's where our end behavior on the left will be shooting down and the end behavior on the right will be shooting up. So down to up. So when x is going to negative infinity, y is going to negative infinity. And when x is going to positive infinity, y is going to positive infinity. For an odd degree polynomial with a negative leading coefficient, here's where the left is going up and the right is going down. So left up, right down. So if x is going to negative infinity, y is going to positive infinity. If x is going to positive infinity, y is going to negative infinity. In this example, we want to use the rational roots theorem to identify all the possible roots of the function. Let's recall that the rational roots theorem is when we have a polynomial and we can find all of the possible rational roots by taking the plus or minus factors of a0, which is typically the last term in our polynomial. It is without a variable, it's our constant, over the factors of an, which is typically the first term in our polynomial. It's the term with the highest degree. So if we take the factors of our constant over the factors of our first term, and simplify them, this will give us all the possible rational roots. So AO in this example is 30, and AN in this example, well, x would have a coefficient of 1 right there. So let's list out all the factors of 30. We have 1, 2, 3, 5, 6, 10, 15, and 30. All the factors of 1, just 1. So here's where we want to put it. AO over AN, and we've got our plus or minus. So plus minus 1 over 1, plus minus 2 over 1, plus minus 3 over 1, okay? If we had other factors down here, we would have to do plus minus 1 over 1, plus minus, and then the other factor. Plus minus 2 over 1, plus minus the other factor, and we would keep going. Basically, this would simplify all of our factors here, would simplify to plus or minus 1, plus or minus 2. Because everything is over 1, we can just say it's plus or minus all of the factors of 30. Here we're going to use the same polynomial and use synthetic division or long division to identify 1, 0 of the function. Let's use synthetic division. I find that a little bit faster. And we're going to test out one of the possible zeros that we found in number 1. So let's test out 2. Let's see if this function has a 0 of 2. So for synthetic division, you're going to list out all of the coefficients in the polynomial. So I've got a leading coefficient of 1, 1, negative 11, negative 5, and 30. And our goal here is to test out this x equaling 2, and hopefully we get a remainder of 0 at the end, and that'll tell us if we've got a factor, a solution. So we're going to bring down the 1. 2 times 1 is 2, and I'm going to add that and get 3. 2 times 3 is 6. I'm going to add that and get negative 5. 2 times negative 5 gives me a negative 10. I'm going to add that together. I get negative 15. 2 times negative 15 gives me a negative 30. When I add that together, I get a 0. So yes, x equaling 2 is a solution, is a root, is a 0 of the function. So we're going to state the remaining polynomial and then find another 0 using synthetic division. So what I've gathered here, now I've got, so here's what we have left. I'm going to put that back into a function. So I have 1x to the third plus 3x squared minus 5x minus 15. So this is my remaining function. I'm going to rewrite this. And then we're going to use this remaining function to find another 0. The reason why we use the remaining function to find another 0 is it's just a little bit easier. It's a little bit faster. Say we were finding the factors of 72. I can break it up into 2 times 36. To find more factors of 72, I don't want to go back to 72 to find more factors. I can then break up 36 and find more factors. This is just a little bit easier because then you're dealing with smaller numbers. So I'm going to test out another possible root. So again, of the ones that we picked in number 1, when we use the rational roots theorem of those possible roots, I'm going to pick another one of those to test it out to see if I get a remainder of 0. So let's test out negative 3. Let's try out negative 3. So I'm going to bring down the 1. 1 times negative 3 gives me negative 3. I'm going to add it. I get 0. 0 times negative 3 is 0. I'm going to add it. I get negative 5. Negative 5 times negative 3 gives me a 15. When I add it, I get 0. So yes, x equaling negative 3 is another possible root. It's another 0. If you tested out a different factor and you didn't get 0, it's okay. It just means that that's not a 0. So you would have to keep testing factors out until you get a remainder of 0. So I'm going to restate the remaining polynomial and find all the remaining zeros of the function. So if I restate what I have here, putting in all of my terms, I now have x to the second plus 0x minus 5. That 0x can go away and just simplify it as x squared minus 5. So finding all the remaining zeros of the function, I can simply just set all of this equal to 0. All right, all the remaining zeros would include plus or minus the square root of 5. So all together, we have x equaling 2, negative 3, and plus or minus the square root of 5. Those are all of our solutions or zeros. What does the degree and leading coefficient tell you about the end behavior of this graph? So rewriting my initial function out, I have the highest degree of 4, so this function has a degree of 4, and the leading coefficient is a positive 1 here. So if the leading coefficient is positive, and we have an even degree, We know that as x goes to negative infinity, y is going to positive infinity. As x is going to positive infinity, y is going to positive infinity. We know that both the ends or the tails of this function will be going up. And that's exactly what's shown if I put this into Desmos and graph it. Just to go over some helpful tips and tricks when you continue on in your assignments to build your roller coaster polynomial. My suggestion when you do a rough sketch, you could also just test out some factors in Desmos. So for example, if you want to type in Desmos, we've got a factor of x minus 1, x plus 3 squared, because you have to have a double root or multiplicity of 2, x plus 5, and then you also have to have like an imaginary root, so maybe x squared plus 1, because if you set this equal to 0, you're going to get a plus or minus the square root of -1, which will then turn into an I. So you can mess around with some of the factors, some of the imaginary factors, to make sure you get everything in there. The reason why my overall equation is negative here is because I know that I want to start down at a level and go up. If you want your roller coaster to look any differently, that's fine. That's up to you. This is your project. You get to create it. Just make sure that you have all of the requirements. When you put everything into standard form, make sure you're going to do, this is technically 3, or x plus 3 times x plus 3, so expand it out. Then you can start your FOIL and distributing everything in, bringing together the like terms. When you find your ultimate degree, once it's in standard form, and then you can determine if your A is positive or negative. This will tell you how your end behavior should look, and make sure you're double checking with how it looks on Desmos. And then you're going to come up with your domain and range. So take a look at all of your x values. Does it go from negative infinity to infinity? Take a look at your y values. What's the maximum or the minimum? Or does it go to, in positive infinity to negative infinity? So you're going to take a look at how your roller coaster is and then determine your domain and range. If you have any questions, you can email me or find me in the VO.